for a moment here. Is it Kalociński?
Kalociński.
Kalociński. Okay, great. Give it. All right, looks like everybody's here. Are you ready to start?
Yep.
Okay, I'm very pleased to introduce Dariusz Kalociński, who will speak on degree spectra of computable functions on natural numbers with standard order.
Thank you. Thank you, Paul, for the introduction. I'm grateful that I can speak at this conference. I'm sorry that I couldn't make it to be there. This talk will be about my joint work with Bazhenov and Wrocławski. And I'll talk about some recent results in computable structure theory, degree spectra, and about a solution to some problem that was open for a couple of years. Let me introduce briefly this topic of degree spectra, which is one of the main topics in computable structure theory. So we'll be looking at computable structure, so a structure like here B with domain B and a bunch of relations R1 to Rn is computable if the domain and the relations are computable. This works for if we have finitely many relations. If there are infinitely many, then we can add some uniformity condition. We can assume that we'll assume that the domain is just a set of natural numbers. So we'll be interested in structures on natural numbers, so-called omega presentations. And a structure A is a computable copy of B if A is computable and isomorphic to B. So this is just to introduce some jargon that will be used throughout the talk. And it will be so we'll consider an additional relation F, which is not in the signature of a structure of the underlying structure. So essentially, if our structure is like looks like this, then we also have this additional relation F. And by F sub A, we'll mean the isomorphic copy of F in a computable copy A of B. So if B is mapped to some to its copy, right? Here we have copies of this relations R1 to Rn, and a copy of isomorphic copy via this isomorphism here of F. And we what the notion of degree spectrum captures is imagine that we are moving between all computable copies A of the structure B. And here, like computable copies of B, and in each of these copies we have an isomorphic copy of F, right? And we are looking at degrees of these copies. So the degree spectrum of a computable relation F on a computable structure B is precisely that, the set of degrees of images of F across all computable copies of B. So this notion essentially captures something like a complexity of a relation which depends on which computable isomorphic copy of the structure we work in. As far as I know, this notion goes back to results by Harizanov. And in this talk, I'll be focused on a particular structure, natural numbers with standard order, and additional relations that we'll be looking at will be unary total computable functions. And the object of study would be degree spectra of this particular computable structure of such computable functions. I'll be using a simplified notation, like here dropping the subscript because I will not consider structures different than that. Okay, and I'd like to show a very simple example. I hope it won't be boring for the audience, to show how going to a different computable copy of a structure can drastically change the complexity of a relation or function. We'll be looking at the structure, and the additional function will be the successor. And we can build a copy of natural numbers with standard order, so that the image of the successor will be Turing equivalent to 0 prime. And we can start with even numbers, and to each number 2n+2, for each number of the form 2n, like these numbers are like standardly ordered, right? But these are only even numbers. And for each number 2n+2, we'll wait for 0 prime n prime to stop, to halt. And if that happens, we will insert a fresh, unused odd number here. And basically, this is the whole construction in a nutshell. And you can easily show that eventually this will be computable, because you just have to, this is equivalent, right? You just have to wait for an appropriate stage at some stage. At some stage S, you will see that X is at that stage less than Y. Each number will eventually appear in the construction, and once it appears, once both these numbers appear in the construction, you know what's the ordering. So it's computable. And you can show that successor, the image of the successor in this copy that we're building here, computes 0 prime, because if you want to know whether n belongs to 0 prime, so you just check whether the successor of 2n is odd, because if it's odd, then it means that the computation stopped. Otherwise, it will be even. And the other direction, like this, follows from a property of this structure, namely that it's delta 2 categorical, which means that for any two computable copies of the structure, there is a delta 2 isomorphism between them. In other words, computable. This isomorphism can be computed in 0 prime. So if you want to compute a successor of X, you just go via this isomorphism to the canonical copy and compute the successor. And again, via delta 2 isomorphism to the successor of X. Okay, yeah. So this shows somehow how switching between computable copies, right, of one structure can drastically change complexity of a relation. And now briefly talk about some known results about degree spectra of this particular structure. And I'll, at the end of this slide, I will point to a direction which I will head towards through the whole talk. So first of all, from the results by Moses from '86, where there is a characterization, syntactic characterization of computable n-ary relations which have trivial degree spectrum. From this, we can derive that unary total computable function has trivial degree spectrum, so consisting of only computable degree, if and only if f is almost identity or almost constant. In 2018, Matthew Wright showed that for a computable unary relation R, its degree spectrum is either trivial or it consists of all delta 2 degrees. So it's either in this picture below, so it's either only a computable degree in the spectrum or already all delta 2 degrees. And in another theorem from the same paper showed that for computable relation n-ary, so here we have unary relations. Now we are considering arbitrarily n-ary relations. Either the degree spectrum is trivial, and if it's not, then it already contains all C degrees. So basically, this result shows that like you can't have any intermediate spectra here. And his question was, can you found a spectrum somewhere in between here? So a spectrum which strictly contains all C degrees and is strictly contained in all delta 2 degrees. And I'll try to convince you in this talk, but at the end, that such a spectrum exists. So I'll be going through some through results that led to the solution. So we considered various restrictions of the class of total computable functions. So one easy theorem was about functions with finite range. So they behave the same as unary relations, which can be seen as functions with finite range, right? If you think about characteristic function. And basically, like almost the same argument like in Wright's paper applies. Let me give you just a brief hint about how it works. So we have a computable function total with finite range. Okay. Suppose that the finite range is contained in these dots, right? Arranged according to the standard order. Like these are natural numbers. We can start the construction from some far enough point, far enough number, far enough so that every guy to the right from this point maps to some element, and these guys have infinite preimages. Some elements can have finite preimages, but from some point on, everyone will land somewhere here. Okay. And the idea is that we want to, so we have a set X, which is delta 2, and we want to code information about this set in the function, in the copy of the function f. So what we want to do is that we'll code the information using even numbers. So the coding will work like this. So n belongs to x when fa, so the copy, right, of 2n lands on, okay, and we have to specify where. Okay, let's say solid and empty element, right? So these are some natural numbers. So it equals this, and otherwise we are sending this to empty circle. Okay, and just what we do is we proceed recursively with recursive approximation of the set X, and whenever we see a change, about n, and belongs, then can be withdrawn from the set and then again put inside. We just push this number further, so 2n lands in some place further, so that the arrow goes to the empty circle according to the coding, right? And so on. So eventually, in this way, we can just push. We push by inserting fresh odd elements, and eventually we get something like that the restriction of this function to odd numbers will be computable, because whenever we put some odd number, we can always, so if we had some odd number here and it was mapped to, let's say, this element, when pushing, we can always find a further point where, like, the direction, like the target of the arrow will be preserved precisely to the same point, and the restriction of fa to even numbers will be a Turing equivalent to X. This is a kind of a pushing, how we call it, pushing to the right technique. This was the technique used by Wright, and it will have a more developed, let's say, more complicated versions for further in the talk. Okay. so these are functions with finite range, but like this property that of this theorem that you have a trivial or delta 2 degrees as a spectrum doesn't hold for functions with infinite range in general. So the canonical example is the successor degree spectrum of the successor consists of precisely all c degrees. And you can actually show this using an argument, a proof along the lines that I presented on this slide. Sorry. Okay, so now we'll be working with functions with infinite range, but so it was hard for us to analyze what's happening in general. So we put some constraints, and we came up with the notion of block functions. Which turned out to be useful in the analysis. So let f be a total computable function, unary, and consider a non-empty interval, of natural numbers. Along with ordering, right, restricted to this set, and along with the function restricted to this set, to this interval, and we call this finite structure an f block if this interval I is closed on f and on, so the function like only within this interval, right? So we cannot have like arrows going from outside, right, or outside. So this is this closure property. Sorry. Okay. And additionally, if we look at the whole structure starting from 0, we want to this part be completely separated from I, in the sense that you cannot have any arrows going outside or inside. So this part is also closed on f and f-1. And okay, and function f is a block function if for every element there is an f block which contains a. And basically these kind of functions can be represented by yeah, we can, from bird's view, you can see like blocks concatenated within each block function behaves somehow, right? And this behavior is referred to as a type, so the isomorphism type of block. And for given a computable block function f, we can sometimes have one-one computable enumeration of its types. It's not always possible to have such a enumeration, but if you, for example, have a function with pairwise non-embeddable types, this is possible. This is one example. Or if you have a function with finitely many types of blocks, it's also possible. Okay, suppose that you have such a 1-1 computable enumeration of types, then you can conveniently represent the function by a sequence of numbers which are names for the type. So in this enumeration, right, we enumerate the first type, then we see some another type, it gets name 2, then you have some another type, maybe then some type repeats, right, and it's 2. So you can represent a block function by a sequence of natural numbers, which denote types. This concept will be important later. Okay, so what happens if we have a block function computable with finitely many types? So we were able to show that such a function has either a trivial degree spectrum or its spectrum is all delta 2 degrees. I will not go into details of the proof, which is which is a bit complicated, because you have to consider a few cases and engage in some combinatorial analysis of the representation of the function in terms of this sequence of types. But let me give you just a hint about the first case, and I'll give you a very simple example. So suppose that so we have finitely many types, right? So let's say that these types are isomorphism. Let's say 3 isomorphism types. Okay. And this case says that there exists 2 words over types. Let's say let it be 1, 2 and 2, 1, and both of them occur infinitely often in the representation of the function. So this could be, for example, let's say this could be 1, okay, type 1, and let's say type 2, and 1, 2 appears infinitely often. So we see like type 1, then immediately after that we see type 2, and in the reverse order as well, right? So type 2 and type 1. Okay. We see this, this and this infinitely often. Okay, and the idea of showing that that you can have any delta 2 degree in a spectrum is that, okay, we have a set X, which is delta 2, and we want to encode somehow the set into the image of the function in our copy that we are constructing. And the idea is that if we have we encode the information about n belonging to X by ensuring that in the construction, number 2n will land on a position like on this position here, right? Of some copy of a finite structure of this form, and n does not belong to X if 2n is eventually here. So basically, this is a variation of the previous argument. So we are working obviously recursively, so we are looking at here. We are looking at approximation, and whenever we find that a change, right, in the approximation, then we so suppose that we have to that it changes that n is withdrawn from the set, right? So currently we have something like this, and 2n encodes information that n belongs to it, but we have to change it. So we push all the elements that are here to the right, and we look for the occurrence of types 2 followed by type 1. And if we find this, we like put the elements on the positions and add 2n lengths on this position. Okay, and basically like based on this, we are able to encode this information. Again, if another change occurs, then we switch this, because this structure appears infinitely often, and we are able to push, right, and encode this information. And eventually we're able to, by looking at the type of thing that 2n occupies, eventually we're able to recover the information about x. Okay, and I will not go into the details of the other cases. It's somehow more I would say complicated version of this argument. Okay, so these were functions with finitely many types. What if we have infinitely many types? One simple example is the function that you see here. So it's a cycle of length 1, then cycle of length 2 and 3 and 4 and so on. Each length of the cycle appears precisely once, and you can easily show that the degree spectrum of such a function is equal to precisely all c degrees. So we see that having infinitely many types can change the situation, right? We don't only have a trivial or delta 2 degrees as a spectrum, but all c degrees can appear as a spectrum. Okay, so we should analyze this somehow. So what was helpful was looking at what we call a counting function. A counting function, so let's say that, let's number these types. So the counting function it says how many times each isomorphism type of block appears in the representation of the function. So if we had some different function here, so if we had some repetition of type 1 here, then this counting function, function. So type 1 occurs, let's say, twice if later on we don't see anything like this. Okay, and this counting function has some interesting properties, which are summarized in the lemma below, which we call the counting lemma. So let f be a computable block function with infinitely many pairwise non-embeddable types, each occurring finitely often. Okay, then the degree of the counting function is a computably enumerable degree. This is the first property. And in addition, for any computable copy A of our structures, I mean we mean here a computable copy A of obviously of natural numbers with standard order. If the image of A in the copy can compute the counting function, degree spectrum of f sub A is also CD. So this is summarized in this picture. So if we have a copy in which FA is above the degree of the counting function, then this degree must be C. And this is something that we used, and that we use in obtaining the solution to Wright's question. Maybe one word about how why if f computes the counting function, the degree spectrum of FA is C. So the idea is that sorry. Okay, we're working in FA with FA in Oracle. We can compute the counting function, so we are able to know how many times a given type appears in the representation of the function. So we just can find types that many occurrences as the counting function says. Because they are non-embeddable, we can we are sure that if we have some type, when we see some type, then it's actually a type, right? And by looking at the canonical copy, we are able to precisely identify how the initial segment in our copy looks like, and therefore we can recover the successor. And because the degree spectrum of the successor is precisely all of C degrees, then then we are done. I mean, the degree spectrum of FA must also be of C degree. So the theorem is that there exists a computable copy. There exists a computable block function f whose spectrum is different from the trivial one, from the set of all C degrees, and from the set of all delta 2 degrees. So this is the solution, right, to Wright's question. And this slide summarizes the main ingredients of the idea of constructing a suitable computable block function. So we construct a computable block function f and a computable copy A of natural numbers with standard order, so that f is made of infinitely many cycles. Actually, each cycle occurs finitely often. So we arrange the construction so that the counting function is incomplete, so strictly below 0 prime. And this is just some variation on Friedberg logic. And we also make sure that there is we make sure that the copy of f in our in A is of non-C degree. basically, the picture looks like this. So we actually construct a computable copy of A in which the copy of A is of non-C degree, and we actually somewhere below the counting function, with the counting function being incomplete. And this actually is enough because okay, why it is enough? So obviously the degree spectrum of the constructed F is not trivial, right? Because it contains a non-C degree. It is not all C degrees for the same reason, because it contains a non-C degree. And it's not all of delta 2 degrees. And to see this, we have to combine the counting lemma that I showed you on the previous slide with the theorem by Cooper, Lamb, and Watson, which says that for any C sets U strictly below V, there is a set C of properly DC degree, such that C is strictly between U and V. So we have to look here, and so CF is of C degree, right? So this is a C degree. But this is also a C degree. So the theorem by Cooper, Lamb, and Watson says that we have a properly DC degree somewhere here. Okay, but by the counting lemma, FA cannot be of this degree for I mean for no copy, right? It can be the case that the copy of F in B is of this DC degree, because for this to happen, FB will have to be above CF, but if FB is above the counting function, then the counting lemma says that the degree of F sub B is C. So it's a contradiction. Yeah, so these are, this is the, like, all the ideas somehow summarized in one slide. And I will try to, I hope that it won't be too demanding for the audience, but I will try to at least hint at some main points of the construction. So we want again, we want FA to be of so wish of non-CE degree, and we essentially use adjusted maybe Cooper's technique for constructing non-C degree, to be precise, properly DC degree. So we have to make sure, so the requirements that we have to make sure that FA doesn't compute WE, and that WE does not compute FA for every I. This would mean that the degree of FA is of non-C degree. So here I will on this in this visual way, I will try to explain how this Cooper's technique can be applied here. So you're looking only in isolation at requirement RE, and I'm not mentioning here many other things that we have to keep track of. So we're building our copy, right? We're building our copy A. So we have built something so far, okay. And now our so this is before initializing our requirement, and now requirement enters the construction. Okay, and have to prepare somehow. So as in Cooper's technique, we choose some witness for this requirement. This witness is a pair of numbers, U and V here. Forget about this. Okay, and what do we do? So we choose appropriate cycles. So this is one cycle, and this is another cycle. This one, suppose that this one, so we choose a cycle. So this one, let's this one be twice as long as this one. It will become clear why it should be that way later. Okay, and we put U at the end. So at the end of the cycle, and V at the beginning of this T1 cycle. So at this point, we know that these are separate cycles. So we know that there is no, so we know that there is, here we know that FA is not equal to. Okay. Okay, and we keep going with the construction, and well, things may become nasty in the sense that we may see that it looks as if our function can be a Turing equivalent to some WB. I mean, we see this in some restricted, obviously in some finite portion, right? How do we see? So we see that something is, so a bad situation is that we see for some finite initial segment, right, of numbers that this equality holds, and we also see that, well, that we can compute using this functional from Wi, can, like, it sends U to V. I mean, sorry. So maybe so this Turing functional using Wi as an oracle sends U to V if and only if in our current approximation of F, F sends U to V as well. Okay. And if this happens, we have to do something. We have to destroy this. Okay. So how do we do this? Okay. So we receive attention for the first time. Okay. We may have by this time something was appended possibly. And what do? We insert fresh numbers in between here. These are gray numbers. We insert those numbers. So we insert these numbers, and we don't don't want to change this part, but just some fresh numbers are put here. Okay, and after the fresh numbers these are numbers. Actually, the numbers that were here are pushed to the right, but we make a slight change here. So we switch the cycles. So the longer cycle comes first, the shorter cycles comes next. This makes u pointing to v by our function. So we are able to destroy this equivalence, and we're happy at this point. Okay, but it may happen that I mean, we see at some later stage that again we have to do something, but because we see this bad situation, and if that happens, okay, it happens. So it happens at some later stage, and we do again the same thing. So we insert fresh numbers here. So these are the gray numbers. And we again recover the previous situation. So the shorter cycle comes first, longer cycle comes next. And so what's important here is that and so there is no obviously arrow going here. So the function f does not send u to v now. And what's important here is somehow a slight, there's a which something that's a slight divergence from Cooper's proof is that we really have to pay attention at the structure at this point. Because why? Because when the requirement receives attention, it uses information contained in this fragment of FA is used in this computation, and we have to recover precisely the same information later, so that this computation can be recovered, and the trick that is involved in Cooper's technique can actually work. Okay. Okay, one last thing that I would like to mention is a slightly broader notion than block function. We call them quasi-block functions. These are functions for which there are arbitrarily long, finite initial segments of omega closed under f, but not necessarily under f-1. An example. Let's say that we send n to a number of divisors of n. If we look at any number, we see that this initial segment is, like every initial segment is closed under f, not necessarily on f-1, because we have some arrows that go outside from right to inside the segment. This is an example of a quasi-block function. And why I'm mentioning this class of function is that this is also that we have proved with Bazhenov and Wrocławski. So the spectrum of a unary total computable non-quasi-block function is equal to OC degrees. So this is something nice that we can have some general theorem like that. Okay, let me summarize with some conclusions and problems. So the main conclusion is that the degree spectra of computable relations on natural numbers with standard order go beyond the spectra that were known so far. So the trivial one, all C degrees and all delta 2 degrees. And this is this kind of weird degree spectrum that you have constructed. Let me mention maybe that this is, so we haven't written that yet, but this is a 99% theorem. So the 99% theorem is that there exists infinitely many degree spectra on the structure, and the idea is that you don't have to. You can arrange a similar construction relative to a fixed C degree. Which then enables you to somehow like deduce that you have infinitely many degree spectra of this sort. Our construction like produced also this C set by Friedberg-Muchnik, and we can just fix the C set, non-computable, and produce a similar spectrum. Okay, then theorem on non-quasi block functions, right? From the previous slide, indicates that if you want to investigate degree spectra restricted to totally unary computable functions on this structure, then you should focus on quasi block functions, because all are have C degrees as the spectrum. So like I think that I can restate roughly I can restate the question by Wright, because like it still stands, but we know more, but we don't know everything, right? So what are the possible degree spectra of computable quasi-block functions, and in general of computable unary relations of the structure? Like this is exactly the same question that Wright posed, but the difference that we know slightly more. And some further directions, maybe we don't know because we haven't tried, but can we transfer techniques used for unary functions to arbitrary unary relations? This is something that can be tried, and also what can be said about the degree spectra if we apply, for example, index set calculation. This is also something that something that was suggested to me in a discussion with Ted Lehman, and I think that's all that I have to say today. Thank you for your attention.
Thank you very much. Any questions? Online, any questions? Do you think you could get, for example, exactly the DCE degrees as one of these spectra?
So, as far as I'm concerned, so I asked this question on in one of my as a question problem is at the end of the presentation, one of the previous presentations. But then I talked to Matthew Harrison Trainer, and he said that in one of his results implies that that it's not possible. If I'm correct, if I recall correctly.
Okay, thank you. Any other questions? Okay, thanks again, Dariusz.
Thank you. Thank you very much.
We will be back